popcorn, a slice of bread, a marshmallow, a spoonful of puffed rice cereal. 4 foods that feel like they're made mostly of nothing. Light, airy, full of holes. And here's the strange thing. Getting air trapped inside food is one of the hardest problems in all of cooking. Each of these solved it a completely different way. One uses a living organism. One uses a machine that beats air in by force. And one was invented by a botanist who sealed grain in a glass tube, heated it, and blew the thing apart. Then fired the result out of cannons at a World's Fair. Same goal, 4 wildly different tricks. Let's start with the one that turns itself inside out. Popcorn looks simple. Heat a kernel, it explodes. But what's actually happening is far weirder. Every popcorn kernel is a tiny sealed pressure vessel. On the outside is a hard, moisture-resistant shell called a pericarp. Inside is starchy endosperm holding water, and the amount of water matters enormously. The sweet spot is right around 13.5% moisture. Too dry and there's nothing to work with. Too wet and it just steams. When you heat the kernel, that trapped water turns to steam. The pericarp is so tough and non-porous that the steam can't escape, so pressure just climbs. Up to about 135 psi, roughly 9 times atmospheric pressure, at around 180 degrees Celsius. Then the shell fails all at once and the superheated starch flashes outward and sets into that white foam. But here's the genuinely surprising part. High-speed cameras in a study published by the Royal Society caught what the kernel does at the instant it bursts. It doesn't just explode in place, it launches itself into the air on a temporary leg of compressed starch that shoots out first, acting like a tiny spring. The kernel actually somersaults. It's less an explosion and more a jump. And this is why popcorn is basically the only corn that pops. Field corn, sweet corn. Their shells are softer and more porous, so steam leaks out before pressure can build. Even within popcorn, the kernels that fail, the old maids left at the bottom of the bowl, usually have a tiny crack or thin spot in the shell that let the steam bleed out too early. Popcorn's whole trick depends on a perfect, flawless seal, which means it can't control the result. You get what the shell gives you. Bread takes the opposite approach. It builds its structure slowly, on purpose. Bread has to do something. Popcorn never attempts. Trap gas inside a soft, wet dough and hold it there without the whole thing collapsing. And the material that holds the air isn't the flour exactly, it's a stretchy network called gluten. When you add water to wheat flour and knead it, 2 proteins link up. Glutenin, which gives the dough its elastic snapback, and gliadin, which gives it stretch. Together they form a web that can hold gas without tearing. Then comes the gas itself, from yeast, a living, single-celled fungus. As it feeds on sugars in the flour, it releases carbon dioxide and a little alcohol. That's biology, not chemistry. Actual living organisms exhaling inside your dough over several hours. Now the surprising part. You'd assume all that carbon dioxide blows fresh bubbles into the dough. It doesn't. Almost no new bubbles form after mixing. Instead, the CO2 dissolves into the dough and diffuses into microscopic air pockets that were already whipped in while you kneaded. The yeast doesn't make holes. It inflates holes that were already there, like blowing up thousands of tiny balloons that the kneading trapped. The final burst comes in the oven. It's called oven spring. As the heat rises, dissolved CO2 comes rushing out of solution and the alcohol evaporates, both expanding fast. One last push of volume before the crust hardens and locks the structure in place. But because bread's air comes from slow fermentation over hours, its bubbles drift and merge unevenly. A long, slow sourdough gets big, wild, irregular holes. A fast, tightly controlled loaf comes out dense and uniform. Either way, it never puffs in a single instant. It's a gradual, living process, which is exactly its limit. What if you wanted to skip the heat and the waiting entirely, and just force the air in? That's the marshmallow. A marshmallow is one of the most stripped-down foods there is. By ingredients, it's basically just sugar, water, air, and a whipping agent, usually gelatin. And notice, air is on that list as a real ingredient, not a byproduct. In a marshmallow, air is the point. Here's what makes it the odd one out. There's no heat-driven expansion at all. Nothing bursts, nothing rises, no steam flashes. A hot sugar and gelatin syrup is simply whipped at high speed, and the whipping alone forces air in until the density drops to as low as 0.2 to 0.7 grams per cc, a fraction of what the syrup weighed to start. You're literally beating air into candy. The whipped air wants to escape. Foam collapses. So gelatin does the real work. In the hot syrup, its protein molecules unfold and wrap each air bubble in a thin elastic film. As the marshmallow cools and sets, those films harden into place, freezing thousands of tiny bubbles right where they are. For a long time, this made marshmallows a fussy, handmade luxury. Then in 1948, Alex Dumas patented the extrusion process, pumped the whipped, aerated mixture through long tubes into continuous ropes, then sliced the ropes into pieces. Suddenly, marshmallows poured out by the millions, and they went from treat to everyday bag on a shelf. But the marshmallow has a hard limit built into it. Take away the gelatin, and there's nothing to hold the air. The foam just deflates back into syrup. Its air is captured mechanically and held by a film. It never seals itself. Our first two heat-triggered foods sealed their own air in automatically. Our last one does too. But instead of waiting for nature, it engineers the explosion on purpose, and it made its debut being fired out of cannons. Puffed rice cereal, those light, crunchy grains, comes from maybe the most dramatic origin story in your pantry. Around 1901, a botanist named Alexander Anderson was experimenting with starch. He sealed moist starch inside a glass tube, heated it hard, then suddenly cracked the tube open. The instant the seal broke, the contents burst outward into puffed starch. He'd discovered puffing. Anderson took it public in spectacular fashion at the 1904 St. Louis World's Fair, firing rice from 8 cannon-like guns. Over the fair, he puffed more than 20,000 pounds of rice and sold 250,000 packages to the crowd. The physics is almost identical to popcorn, with one key difference. In gun puffing, whole rice grains go into a sealed, rotating steel chamber and are heated under steam pressure of around 150 to 200 psi. Then the chamber is suddenly opened. The instant the pressure drops, the moisture inside each grain flashes to steam and expands the kernel almost instantly, roughly doubling its length and width, puffing it several times over in volume. But rice can't do this on its own. Unlike popcorn's naturally moist kernel, raw rice is too dry to puff. It has to be conditioned with steam first to load in moisture. And unlike popcorn, the grain has no tough shell to build the pressure. So the machine becomes the shell. The steel chamber holds the pressure, and opening it is the deliberate structural failure that triggers the burst. Quaker Oats leaned all the way into the strangeness, branding the cereal, the grain that is shot from guns, and running 1930s ads, showing rice literally blasting from cannons. But the guns had a catch. Puffing one batch at a time was slow. After World War II, continuous machines took over, and by the 1970s, most makers had switched to extrusion lines that cook, puff, and shape grain in one non-stop flow. So 4 airy foods, and by now you can see the shared blueprint underneath all of them. Trap a gas inside an edible matrix that's strong enough to hold it, but stretchy enough to expand. That part they all share. What's different every time is where the gas comes from. Popcorn and puffed rice use flash-expanded steam, sealed moisture exploding into vapor. In fact, they're nearly identical physics. The only real difference is that popcorn's breaking point is a natural flaw in its own shell, while puffed rice's is a steel machine engineered to pop on command. Bread's gas is alive. Carbon dioxide breathed out by yeast over hours, which is why its holes are big and irregular instead of instant. And the marshmallow stands alone. No transformation, no heat trick, just air beaten in by force and trapped in a film. Next time you eat something light, ask the real question: where did the air come from?